in there, so please take advantage of that. So I'm going to take us up to lunchtime. I have that enviable or not enviable position between being between you and lunch. I think the first time I ever said that. All right. So starting off with a bit of context, why consider motors and pumps? Well, motors do consume a lot of electricity. And induction motors typically that we'll have in healthcare are about 90% of the total of all motors out there in industrialized societies or Western industrialized societies. So because of the large consumption of energy, it suggests it's an opportunity. Past engineering practice has typically oversized things, systems to the load, and we'll talk what the load means in a few minutes. So that ultimately probably presents an opportunity as well. We need to go back and right size. I think in energy, right sizing is one of those areas where it makes a lot of sense, with considerations like not dropping your pressure too low as in a boiler, and the same thing can occur in pumps too, or an analogous situation. The last 2 points here I think are important. Over 25 years, if you look at 25-year life of a motor and a pump system, the initial cost of a drive, motor, and pump is typically less than 5% of the energy operating cost or the operating cost of that particular system. So that really asks us to look at operating efficiency. But when you look at like maintenance of that pump too, that's another piece I would add in here, and I'm going to speak to that in a few minutes. So operating a pump inefficiently will also result in probably reduced reliability as well. And so there's a dual win on this one. Now, the other thing, when it comes to the motor and pump, 80% of the energy passes through the motor or more. So is the motor the problem, or is it what the motor is connected to, what we call the driven system? Is the pump the problem, or is it the driven system? So I'm going to focus us on moving towards where we need I'd call it the fluid power ultimately, and work our way back up through the system. There may be all-encompassing things we can do, but we have to focus on the driven system and all the way out to the end of the driven system. To that end, I'm going to start us from in that context. Here we have a pumping system which is provided with electricity from a utility meter via distribution system. We got the motor which converts electrical to mechanical energy. We have a close coupled motor to a pump, or pump to a motor. We got the bearings in there. Then we have the pump that actually, the centrifugal pump is shown, which creates flow in a loop. And ultimately we need flow between those two heat exchangers to move heat between, from the source to the sink heat exchanger. But in the middle of all that, in addition to the pump, we've got a flow control valve of some sort. Even if it's fully open, might be introducing a bit of friction in there. And we have a piping network. And I always like to say, where are the best opportunities? Well, I'm going to argue the best opportunities are deep down in the system, and I'm going to show how we do that. The next question I'm going to ask you is, what's the overall efficiency of this system? Going from electricity, right, at that meter, all the way over to water power, which is really to overcome, the pressure difference between those two heat exchangers and move fluid properly to carry heat. So what's the overall efficiency of that system? Or how do we calculate it? Anybody want to take a stab at that one? Well, I give you all the component efficiency. What's that?
I guess I'm not allowed. I know the answer.
Well, yeah, exactly. Well, anybody else want to take a stab at it? There's all the component efficiencies, and they don't look too bad. They could be higher in a few places. Well, the answer is you multiply them all together. And when you do that, you basically get a very low efficiency. So, it's kind of like you got a funnel with holes in it, and you lose a little bit at each step. But at the end of the day, these are not bad efficiencies. So replacing that motor with a more efficient motor, how much effect would that have? Not very much. How about avoiding that valve? Or how about removing some friction in that pumping loop? How much impact would that have? Well, I want to go step outside of the healthcare sector for just a moment to another sector which have a lot of pumps. And I want to step into a situation where it was a manufacturing plant being designed. It had about 90 horsepower of pumps in the original design. And they asked the designers to go back and think about the size of the pipe, right? And the bends and turns in the pipe. So the friction in the driven system being the piping network. When they did that, they started off with 92 horsepower, as I said, but then the final design, which was optimized for energy, was 7 horsepower of mover, basically in that system. That is an incredible difference. So, you might have been thinking, well, Steve, this is nice theory, because people have said that before, or is it great practice? Nice in theory, but if you can put it into practice, so those nice swept elbows, right, things like that, larger pipe. Now, granted, the larger pipe's going to cost more, better piping practice is going to cost more. But when you think about the fact that the cost of energy in one of these systems is 20 to 30 times as much as the cost of the initial system, it might just make sense to do it. If you want to read more about that one, there's an article at RockyMountainInstitute.org called Big Pipes, Small Pumps, because the practice years ago was small pipes, big pumps when energy was cheap. So the idea here is we need to dig down in the driven system. And that's kind of the approach we're going to take moving forward. Now,
and let's say they would not have changed it. It would have stayed at 92. 92 is calculated by the engineer. Once they go on site, I can bet you the engineer covered himself up. He actually overestimated the pressure drop. So they're not going to change the pump. They're just going to add artificial pressure drop to basically match the engine. They'll throttle that valve that you were showing. They will throttle the valve. So this actually is very critical because they will actually size the pump, size the motor for a calculated value. And I can bet you all your pumps in all your buildings are oversized because of that.
Interesting. Yeah. Now, in this particular story, the designer was forced to go back and do it properly, right? But you're right. If that's not enforced or caused to happen, you're probably going to end up with an oversized system, which is one of the points I made in the first slide. Absolutely correct. Absolutely correct. And I'll show you an easy way to get around an oversized system, but isn't efficient. We all know what that is. So I'm going to start off with the motors. I want to say a few words about motors because motors are part of the system. Typically, motors are sized. You want to size them to run in that 65 to 100% range. You don't want to size them way over range, and especially in small motors. In the 65 to 100% range, the efficiency of most motors is relatively flat. It doesn't change dramatically, but because a motor has fixed losses, and the smaller the motor, the greater the fixed losses due to the certain aspects of the design, the efficiencies drop off when you get down in that 25% range. So if you do have a motor that's way oversized to its load, to its pump, and you know that for sure, and you know it's not a variable load on that pump of any sort, then you might want to consider resizing that motor to the pump. But I would never start with the motor in terms of changing it. To me, that's the last consideration. So if you work our way back up, and we've got a smaller pump, and now our motor's too big, that's when we want to consider that. And there could be some improvements there. But we got to be careful because if we go to a smaller motors are inherently less efficient to begin with. And sometimes you can end up resizing to a smaller motor and actually having lower efficiency, even though it's higher loaded. So it's a bit of a tricky one. Another one to watch out for is if you've got an old motor and you go and it's driving a centrifugal pump and you move to an energy efficient or a premium efficiency motor. Today you would be buying a premium efficiency motor. You may just find that motor spins faster afterwards. And due to the laws that I'm going to show you in a few slides, the pump affinity laws, you're now going to be consuming more power. So a 1% speed increase, right, on the shaft of that pump can actually create a requirement for 3.5% more power. And if you're only going to get 2 or 3% of efficiency improvement out of that new motor, guess what? You now are back from where you started. So you've got to be really careful looking at it from the motor moving forward. You've got to really go to the load and work your way back up, and then you'll end up in the right situation. Motors do suffer from poor operating conditions, no doubt about it. So the number one or leading cause of motor failure is heat from a number of different sources. Keeping them clean, keeping the voltage balanced. If you look on the right-hand side, anything you do to the voltage applied to a motor will reduce its operating efficiency if you move off the nameplate efficiency. Too many starts without a soft start. All of those things lead to a reduction in the motor's life. And it only takes a 10°C rise over the rated temperature of that motor for it to reduce its life by half. So, I mean, again, if you've got motors that are failing, you've got to do the post-mortem on them and make sure we understand why, right? Just replacing with a new motor, and in fact, a new motor may actually be more susceptible to those poor conditions. Even though that new motor might be premium efficiency, it may be more susceptible to the poor conditions than the older motor. So we've got to understand if a motor is failing, if it's overheating, what is it? We got to fix it, go for root cause, and that will inevitably lead, because heat is not power, shaft power, that's going to lead to a more efficient motor if we cause it to run cooler.
And if somebody
go ahead, Michelle.
Yeah, I was going to say, somebody had throttling valve, they decided to just open on their motors, and they see that their motors start burning out. That could be a reason, because they are actually, by removing pressure drop, you may actually end up overloading your motor.
We'll look at that in a second. I've got a slide that looks at that. That's right. The best way to kill a motor is to driving a pump, or a fan for that matter, is to basically reduce the pressure drop they're working into, or the pressure it's working into. It causes the pump to work harder, the motor to work harder, overload the motor. Absolutely. I actually saw that in a complete outside a hospital in a potato warehouse. They had 2 fans, and we're going to do an energy audit there. So the day before we went to do the energy audit, they turned off one of the fans because they thought maybe that was a smart thing to do. By the time we got there, they burned out the second fan because those 2 fans could maintain pressure through ventilating the potato warehouse, but the 1 fan couldn't, right? And it just worked itself to death. Within 24 hours, right, it killed itself. So that's a very real thing. Works in pumps too. So when it comes to rewinding motors, it does make sense, okay? But we've got to be careful. The problem we have when we do a motor rewind is that the motor has to be baked out in order to remove all the varnish and the old wire. And when they bake it, if they don't control the temperature very, very closely, you can end up changing the properties of the iron in the motor, and that ends up reducing its efficiency in almost every case. A good motor shop can stick within 1%, but it could be as much as 5% per rewind, and it is somewhat accumulative as well. So make sure that if you're getting motors rewound, you get a core test before and after to demonstrate how that core hasn't changed, and put some limits on it. If it comes back too low, then you basically don't want that. You're not going to pay for that rewind. So on motors, you know, kind of helpful hints are maintaining the motor in good running conditions, balancing the 3 phases, right? If you've got a voltages to a motor that's inherently imbalanced, that will create heat in the motor as well. Certainly, we can improve reduce the line current to a motor by using power factor correction, things like we talked about in the previous section. But watching those rewinds, and then ultimately looking at what's going on downstream, and that's where we're going next. So don't oversize the motor, right? Because that makes for inefficiency. Don't oversize the pump, and you know, typically that's what you end up with, is an oversized pump and a motor. Undersizing, yeah, that can definitely lead to shortening of life, but that's where having things like speed control can help you, because you can deal with a high requirement and a short or a low requirement within the same system, and not strain it either way, either in the, you know, the overloading it or oversizing it in that sense. And typically, yeah, you want to work within that 60 to 80% loading on that motor. So we're going to turn our attention to pumps, because I think there's a lot more opportunity with pumps. Honestly, I've changed motors to get efficiency improvements. I've gone out and changed motors to get efficiency improvements. We did a little experiment a number of years ago. We put more efficient motors in there, but we ended up in 9 out of 10 of the replacements that we did, taking them out and putting the old motor back, because it was the driven system that really dictated what was going on. So don't start with the motor. I've done it, and I've had to literally change motors out to fix the things that we created by putting them in. So it's not a good idea. Got to look to the driven system, right? The driven system in a motor and fan system, it's gonna, yeah, there we go. In a motor, or sorry, a pump and a fan system, they're basically the same principles. We're going to talk about pumps today, but the same principles apply to fans ultimately. And basically, on the little picture on the right-hand side is, you've probably seen this before. Many of you have seen this before. It's the curve, or the performance curve, that relates where the equipment wants to operate, where that pump wants to operate, relating pressure to flow. So it wants to operate somewhere on this line. And then the system that the pump is literally forcing fluid into then responds by putting up a pressure, you know, a resistance to that flow. And the system wants to operate on this dotted red line or orange line here. And where these two cross is where the pump and the system decide they're going to operate. They come to an agreement, and that's where it's going to operate. And that has implications for the amount of power, the efficiency, and the amount of power the motor has to provide as well. Now, for changes in speed of the pump, right, we know that the flow varies according to the speed. That is, if you want double the flow, in simple terms, you double the speed of the pump itself, spin it faster. Now, if you want double the pressure, you actually have to look at the relationship. You realize that, right? So if you double the speed, you actually generate 4 times the pressure difference. So if we have a pressure requirement, we have to look at the second relationship. But the consequence of all of this, if we're trying to get pressure and flow, right, is that, right, for a change in speed or flow, right, we end up with a cubic relationship between the old and the new speed and the old and the new power. i.e. if we want to double the flow, this implies we need 8 times as much power for a given system to get that same flow through it. That's a big difference, and that's a relationship that gets in your way when you're changing to more efficient motors that spin faster, because in that relationship, a 1.1% speed increase, which may be a function of a stronger and a better motor, ends up with a 3.5% power increase, and that can really kick you in the pants if you're not careful. So ultimately, we need to be aware of these rules. Now, most people have probably experienced these relationships firsthand. If you don't believe them, think about driving down the road or walking on the beach, for example, and walking into the water, and you could walk through the water, not a problem. But let's say that your kid or your grandkid or something over there happens and you have to run to help somebody. Try to run through the water, which is about double the speed of walking. If you double your speed through the water, it's almost impossible to move your feet through the water, your legs through the water. And that's the relationship that you're up against, called the Newtonian fluid. But you know what? We cause impellers to do that all the time. Now, the relationship overall for the power required is a product of the pressure and the flow, or the pressure and the differential pressure and the flow. So any operating point on this curve over here on the right-hand side, we can calculate the power based on the pressure and flow implied. And I'm going to come back to that one in a few minutes. So if I move ahead from this, we want to say a couple things about head or pressure, because we have two kinds of systems that we might be working with. We might be working with a closed system whereby, right, the relationship between pressure and flow follows this dotted line here. So at no flow, there's no resistance. The system doesn't put up any resistance. So there's no pressure or head. Head difference and pressure we consider to be the same thing. But when it comes to an open system, say we're moving water, right, up to a cooling tower, right, that system is open because we don't have the benefit of the water coming back, right, to give us back the head or the rise in height. At that point, right, there's going to be, no matter what the flow is, right at zero flow, there's a head difference or a pressure difference between the source and the destination. So ultimately, the system curve doesn't come back to the 0 point on the pressure flow relationship. And that has implications when it comes to applying speed control, which is where we're heading with all this in these types of systems. Meaning that it will reduce the requirement or reduce the opportunity for speed control. Because we have a requirement for pressure, we have to maintain a certain amount of speed in order to overcome that pressure, in order to move water up that hill. It doesn't go to 0. So we can't.
To that point,
go ahead.
Some clients that had a high-rise building and they did not know about open systems, static lift, and they thought the pump needed to work more because it was going, 20 stories high. But what they did not get is that it's coming down 20 stories and it's pushing the water back up. So,
yeah, I always tell people, if you got a pump here and the top of the loop is here and you're running it around, whether you run it this way or this way, right? It doesn't matter. It's the same friction in the pipe, which is all you're looking at, is what's called the friction head, and basically what goes up comes down. So there's no difference in what the pump will experience in those situations, as long as the system is closed. If the system's open, completely different story. Absolutely. So we need speed in a pump to generate pressure in order to move water through a static head or lift. But if it's a closed system, that doesn't apply. So for any given device like a pump, there is a relationship then between head or pressure and flow. And typically we'll have pump curves, and on those pump curves, it'll show us, we might have one line, which is the only curve for this pump. But you know what? There's 4 lines on this pump. And in fact, if we change impellers in a pump, we can achieve, right, basically make it into a different pump. So a lot of times people say, well, I need a smaller pump. Well, no, maybe you just need a smaller impeller to achieve the lower flow, right, at, with a smaller diameter impeller. So whether it's the speed of the pump or the diameter of the impeller, that's a very similar relationship. But ultimately, as we change that pump, we end up with different operating efficiencies. So if we were, say, concentrating on this one line here, we'll see that if we operate right in the middle of this little center, I call these egg-shaped curves, so we're probably north of 80% efficiency on that pump. But as we move, right, to higher heads, meaning to higher pressures, meaning to, as we throttle that pump, we're actually going to move. So if we throttle that pump to 50% of flow, we've dropped from, say, 82% to probably 65 or 65% 3% efficiency. That's a dramatic drop for just closing a valve. And if we go further at 50, right? And if we go even further, not only do we drop efficiency, but we're probably going to destroy that pump. And I'll show you what can happen in a few minutes. Now, likewise, if we push the pump higher, that is, if we use more speed to get more flow, right? Or we reduce the head on the system, the pump will try to operate up here, because if we reduce the head on the system, we're going to move up there as well. That's going to cause trouble as well. So in terms of efficiency, but on the next slide, what we'll learn is, this is a wonderful slide. What we'll learn is there's a strong relationship between what's efficient and what's reliable. So this is actually taken from a website, I think you can see it at the bottom there, craneengineering.net. And they have got some neat videos up there. I don't even know those guys, but I've used their website a few times. But they actually have recreated what they call the pump reliability curve. So here's your head and here's your flow, right? And here's your pump curve moving across like it does, right? And then they've looked at, this is their best efficiency point, but now they plot on this the reliability curve. And they show you then, so as you move away from the best efficiency point, as you're moving to those egg-shaped circles that are lower in efficiency, things are happening, right? So you're getting things that will reduce the life of the impeller, like cavitation, and if it's really badly throttled, you'll end up creating high temperature rise because the pump can't even cool itself, right? And the same thing goes if you move the pump on the other end of the curve too. So I'm going to get into, if you haven't seen cavitation, most of you probably know what cavitation is, but lower bearing and seal life, right? It was funny because I went to a chap in a hospital a while ago, and I said to him, you guys put new drives in the hospital here on these pumps. What do you think about the energy savings? And he basically said, I really don't know what the energy savings are. He said, but I've avoided, I think I mentioned this one before, I've avoided 2 pump seal replacements in the last year. So that's a direct sort of demonstration of what this chart is all about. So to me, efficiency and reliability go hand in hand. If we treat a pump properly, it's going to operate efficiently. If we treat it improperly, the fugitive energy that we're using inefficiently, and that's what's doing all this damage. It's the energy that we're not converting to flow that we really need. Some people call that fugitive energy. So, good way to look for an opportunity for modifying the efficiency of a pump system to get better efficiency is to go look for your least reliable pumping systems. If you've got ones that are chronically requiring some of these things or suffering from these problems, those are probably the ones that are going to be operating at lower efficiency. And so now you get that dual benefit. So I just like Paul said, look at it from a maintenance perspective. Look at it from a maintenance perspective. Look for the pumps that you have to do more maintenance on, and maybe they're going to be the ones that are going to give you more efficiency if you treat them better in the long run.
And by the way, this is not hard to obtain. All you need to measure is the delta P across your pump. If you know the model of your pump and you measure the delta P, you can figure out where you are on the curve. It's a very, very easy measurement to take, as long as you can find a pump curve. If you don't have a pump curve, you can actually build one by a simple test, but you can figure out where you are on the pump curve if you're far off that best efficiency point.
Now, sometimes pump curves change, and they change because the pumps change. On the left-hand side here, we see an impeller that looks like it's being eroded by particulate matter, but in fact, it's being cavitated by the water flashing to steam because the pressure conditions aren't right at the inlets of the pump. So you get these bubbles of vapor, right, that form in the water. And as those bubbles arrive at the impeller after coming in the inlet, they in fact then collapse back to water, and with that collapsing causes an erosion of the impeller. We call that cavitation. And this is purely a function of the incorrect operating condition, what we call not enough net positive suction head. And as the temperature of the water rises, you can imagine its propensity to flash to steam or to vapor actually increases. So you need more net positive suction head on a warm water than a cold water system. So ultimately, I mean, the operating conditions can make a huge difference, and that impeller will not behave like the original pump curve would predict. So checking your pumps to see where they're operating is going to be critical. The other thing that can happen is the system can change. Now this is a small, I think, a 4-inch pipe that had precipitate built up over time. So the 4-inch pipe became a 1-inch pipe. Years and years ago, I had a gentleman come to a workshop that we did, and he had a photograph, and I wish I had taken a picture of it at the time. He had this little 4x6 photograph of a chiller, an 8-inch pipe on a chiller and on chill water system, and he had the same kind of constriction. Now, this was from a dairy, but he was in a hospital. So it's not unusual. It's not impossible to have that occur. Now, that's pretty extreme, but that's going to make that system curve get very, very steep. And that's going to cause that, well, if the system curve gets steeper, you're basically throttling the pump, whether you think you are or not. It was funny because I found that piece of metal on the electrical maintenance manager's desk, and he said, I got this because they wanted me to put a bigger motor on this pump, and I said, there's something wrong here. So we cut the pipe apart, and we discovered that it had nothing to do with the pump. It had everything to do with the pipe itself. So ultimately, then we can change those system curves, when we change the system, right? So a dirty one will actually exhibit a steeper system curve, and these are all for closed systems. And then we have a worn impeller, which actually becomes basically a less efficient pump, and a pump with a different pressure flow characteristic. So,
And if you have a cooling tower, that's the pump you should be listening to in terms of cavitation. They're usually the one that have more problems with cavitation because they're open systems. So cooling tower pumps, listen to them. If you think you hear sand going through it, it's probably cavitation.
Cavitation, absolutely. So when it comes to actually applying flow control to a system, I mean, we have to do it with respect to what's happening underneath. So it's not just a matter of whipping a variable speed drive on a motor driving a pump and okay, we're all good here. We need to understand what we're trying to achieve. So ultimately, right, we might be now operating, say at this point with this flow on this particular pump, and we want to reduce the flow. So maybe we want to reduce the flow by 1/3. So we close that valve and we throttle it. Or maybe this happens accidentally. One way or the other, if we restrict that pump, no matter how we restrict it, we're going to move up that pump curve. So we move to that throttle point, right? But if we're throttling and we can remove the throttling by using speed reduction, that is, half speed, third speed to get half flow, quarter flow, then we would basically be moving down the system curve. So, and remember, the power required at the red and the green points is the flow times the pressure. So at the red point, the flow times the pressure is probably more than double what it is at the green point. So the opportunity then is, as on the slide on the right, is this converts itself to a situation whereas if we throttle a pump, we will reduce the power. There's no doubt, mildly reduce the power. But if we speed control a pump, we'll follow that system curve down, right? And we'll see much more significant reduction in power overall. So what I want to do just to finish off before lunch is to actually demonstrate this firsthand. So I'm going to take down my slides here, and you're going to see a great little probably sunset picture in a second. And I'm going to open up this is my electronic flip chart. It's actually a spreadsheet connected to a flow meter or to a power meter that's driving a little pumping system I'm going to show you in a second. So I'm just going to start up my connection to this system. Here we go. So right now it's showing 0 watts. I'm just going to test it. I'm going to turn my pump on, and I can actually see the wattage. Now I want to see the pump, Steve. Okay, let me show you the pump, folks. I'm going to turn off my camera because I can only allowed to have one camera on at a time here. So I'm going to turn on my pump camera now. This is pump cam. And I'm just going to make this a little easier to see here. So let me just set the aspect ratio to 4:3. Actually, aspect ratio 16:9. And I'm going to crop it down. It'll make it a little. There we go. So here's my little pumping system on the table beside me. And just to let you know, I'm here. I'm waving at you. Okay. So what I'm going to do first of all, and I'm going to run this pump through its paces. So I've got a little pump here, which it's actually an ECM motor in the pump, and it actually has a number of different settings, but I'm going to use the fixed speed settings on it. It does have an adaptive mode. Most manufacturers have a pump of this size that does this, but I'm not going to use that particular mode. I'm simply going to set it to a full speed, which is what I'll do right now. Okay, and that pump is now running in full speed mode. Okay, and ultimately you can see my little flow meter here. It's just a little plunger, and as you can see I'm varying the flow, and this is my valve. So I've got 3 points. I have 8 gallons a minute, 5 gallons a minute, and 2 gallons a minute. So that's what we're going to do. We're going to try to achieve different flows: 8 gallons a minute, 5 gallons a minute, and 2 gallons a minute. Right? Right now, I'm doing it right at the 8 gallons a minute. The valve's open, and we're using about 44.5 watts. So I'm going to grab that value. So what my spreadsheet calculates for me now is the power required to generate that flow per gallon per minute. So it's 5.6 watts per GPM. All right. So now what I'm going to do is do probably not the best thing, but I'm going to use the parking brake here today. Actually, I'm going to use the throttling valve. Okay, I'm throttled back to 5 gallons a minute. There's a little bit of parallax on your thing here, but if I look right over top, it's actually right on the 5 gallon per minute line. And holy mackerel, my power actually maybe even gone up a little bit. The voltage is probably jumping around, but the power definitely hasn't dropped. All right, so in this pumping system, it's not even dropping. I mean, now if I were to use a non-ECM motor without an electronic drive on it, you might see a mild drop in power. But this one actually, it has a nice speed controller, which I can use as a second part, which works a lot better. So now I'm going to drop back to 2 gallons a minute. You know, so we're down a little bit, okay? I mean, you know, but we're basically running the same power to do the same thing. So it's funny, I've seen these pumps in hydronic systems. This particular pump with a throttling valve on it, and the pump was set to the full speed like it is now. So that pump is still running at full speed. The noise you heard was actually the rattling of the spring in this pump. But I mean, now which one do you want to pay for? Well, you're not getting much flow out of this one, and you're paying a lot for the power. What we're going to do next is we're going to go to full flow, and I'm actually just going to set it down to the lower speed. So the flow settles back, right, to the 5 gallons a minute. And now our pump power is dropped to 21 watts. Drop that in here for 5 gallons a minute, 4 point. So we're actually, in this case, in fact, we're operating a little more efficiently than we were before, maybe because we moved that pump to a better operating point. Okay, let's try it again. We're going to drop now to 2 gallons a minute, right? So I'm going to set the pump down to 2 gallons a minute, right down here at 2 gallons a minute. I'm going to enter the power here, or the flow here. And now we're sitting at 6.2 watts. So your choice. You can get 2 gallons a minute with the valve, or you can get it with speed control. Now, if you need pressure, we got to be careful here, right? If we need pressure, we may not be able to go that low. So in an open system, right, where pressure is required, or if we have valves in the system, we have to be a little careful that we don't drop below it. So there are going to be limits to how much we can speed reduce the system, because the throttling in the system may be a result of zone valves and different things within the system. So, I mean, I've simplified the situation here, but I think it goes to show how quite clearly by applying speed control, we can see a dramatic drop in power. And that's where I'll leave the demonstration, Paul, not Paul, but Michelle, did you want to add anything to that one? I know you always get excited about this little demonstration.
Yeah, well, since you've upgraded the motor, that has such a large impact on the watt per GPM. The best example for the pressure-driven system is a booster pump. Always be careful. A booster pump, you may not be able to drop a lot because you need pressure to get that water all the way up to the upper floor. The other thing is, now you saw there was a throttled valve. When Steve was throttling the valve, you could see that the power did not change. If I were you, I would check every pump I have in the building, see if they have a throttling valve. If they have a throttling valve, and they usually all have a throttling valve, obviously you'll check, is it partially closed or not? If it's partially closed, that's right there. That's the red light. That's a potential measure. You need to probably do a very simple pump test where you will check what the savings could be from adding a VFD. And we're not talking changing the system to variable flow. We're using the VFD just like Steve did here, just to modulate the flow back to the proper flow, but with no throttling. If you have a throttling valve and there is no VFD and the throttling valve is fully open, it is very likely that you're over pumping your system. Somebody saw a throttling valve, heard it was not good to have a throttling valve partially closed, they opened it up. What happens then is that your flow will increase and you will not be saving. So not having a closed throttling valve does not mean you have no savings potential. Very often that means you've got too much flow. The best way to check that is obviously a pump test, but you can also look at your delta T. If it's a chiller system or a heating system or a cooling tower, you check between the supply and return temperature. And if you've got a very low temperature differential, such as 1 or 2 or 3 degrees Celsius, that's a very low delta T, regardless of the type of loop that you have. That's a sign that you're over pumping. And you'd be sometimes even better off to throttle the system, even though the example we saw, there was not much change. Sometimes you do save a little bit, but honestly, that would mean put a VFD just like the demo we just saw. And you saw we went from 22.2 watts per GPM to 3.1 watts per GPM for the 2-gallon example. So check your pumps. Low delta T's throttle valve will have the same impact as the demo Stephen just gave us.
Yeah, I'm glad you brought the thing up with the delta T, because sometimes the delta T problem can lead you back to ultimately another problem or another opportunity as well. So you solve two things in one. Yeah, absolutely. And what about the valve that's not a throttling valve but gets used for that and kind of lurks and hides away? What's that called?
The
triple duty valve?
The circuit balancing valve?
Or the triple duty valve?
Oh, the triple duty valve, yeah. So the triple duty valve, you will not remove the triple duty valve, by the way. You will keep the triple duty valve because it has triple duty, but you will open it up completely and check the number of rings. The triple duty valve, I don't have a picture here. If you've never seen it, it's got typically it's a stem and you see rings on the stem. And the number of rings that you see typically relates to the size of the valve. And if you know it's a 4-inch or a 6 or 8-inch valve, you'll know how many rings you should be seeing. And again, make sure that it's completely open. If you don't, mark it where it is right now, take a wrench and see if it opens up. If it opens up, it means it's throttled. And the reason I say mark it up, because you want to bring it back to where it was. Don't do any kind of test without being able to bring it back where it was. Otherwise, you may actually burn out your motor, because sometimes by opening the valve, you have more flow, which can, depending on the pump, create more power and overheat your motor. So triple duty valve is something you have to keep an eye on. And then you get your circuit balancing valve. If all your circuits are all partially closed, that means one should be open and the other one partially closed. So you always have to be careful. As soon as you see closed valve, that's a indicator to dig into that system.
All right, well, we got 3 minutes to lunch, so we successfully navigated to that point. Are there any questions?
Well, then
Yes.
I'll just tell another hint that another thing we have not talked about as soon as you talked about pumping. If you have to prioritize, condensing tower pumps are usually your largest and should be looked at. They're open system pumps. They're subject to potential cavitation. They should be #1 on your list of investigation. Chilled water pumps should be #2 because they are larger. The reason they're always larger than heating pumps is because the delta T between the chilled water and the set point you want to achieve in the room is small. So you have larger pumps, and every time you save a kilowatt hour of electricity in the pump, you will save maybe 0.3 kilowatt hour for the chiller. So there is an interactive effect where you save pump power, you will save cooling energy, and you will save a little bit of tower energy. So that's why cooling tower should be your first priority. Chilled water should be then, and heating pumps, I'm not saying to neglect them, far from that, but they will be smaller because of the greater temperature differential. So you will, so you'll usually have smaller pumps. So you would look at those after you've already done your homework on the cooling tower and the chilled water pumps.
All right, any questions for Stephen or Michelle on the motors and pumps? Seeing none or hearing none, thank you very much, Stephen, and thank you very much, Michelle. We'll come back at 1 o'clock. This afternoon, we're going to cover compressor systems, and we have somebody with some firsthand experience that will give us a very exciting and thorough presentation, I'm sure. We'll also look at building envelope and renewables. So if everybody wants to break, go for lunch, and we'll be back at 1 o'clock. Thank you.
Great. Thanks, JJ. See you, everybody.
Thank you.
We'll leave the platform open, just be just as easy. So rather than trying to log back in, you can just leave your connection and everything should work fine.
Good idea.